Hello everyone. In this video we will introduce the idea of partial fractions. Alright, to motivate why we care about partial fractions, take a look at these two integrals. Which of these looks easier? So the one on the left looks like maybe you could do u sub, but you would get 2x plus 7, and that is not a multiple of x plus 14. So u sub doesn't work. And even if you break it into x plus 2 and x plus 5, this isn't really helpful in any way. We get no cancellation. On the other hand, hopefully you selected this one on the right. So this one works out nicely, right? So something over x plus 5, you just do a quick u sub with u equal to the denominator in any of these. You get negative 3 times the natural log of x plus 5 plus 4 times the natural log of x plus 2, and of course plus c. So this one on the right was much easier. Well, it turns out that these are actually the same. And it's partial fractions that will help us get into the form on the right where our integration is much easier. So here's a little fact. So every polynomial can actually be factored into all linear or quadratic factors. So just a little example of what I mean by a quadratic factor, right? If you have like x squared plus 1, we know that can't be broken down anymore. And so we would call this irreducible. But a lot of the time, right, we can factor all the way down to like an x minus 2 or whatever. Now, if we get down to all linear factors and they're distinct, right, it's not like x plus 2 times x plus 2. If we have different roots, then it turns out you can split this as some constant over the first factor plus some other constant over the second factor. There are other cases that are a bit more complicated, but we'll get to that later. So let's figure out how to find this a and this b first. Okay, so if you see something that looks like this algebraically, you should be distressed at the notion of how many denominators we have, and all of them are different. So one option is to just clear all these denominators. So we just multiply through by x plus 5 times x plus 2. And the result is we get x plus 14 is a times x plus 2 plus b times x plus 5. And we should note here, right, this is true for any x. And we're going to take advantage of this fact. Okay, so if we want to solve for a or solve for b, well, the easiest way to do it is to make one of these two pieces 0 so that one of them disappears and we can solve for the other. So we look at the roots and we're like, okay, if x is negative 2, what does this statement say? It says that negative 2 plus 14 or 12 is, well, this goes away, right? Because x plus 2 is 0 if x is negative 2 plus b times 3, or 3b. Well, 3b equals 12, this means b is 4. And similarly, if we want to figure out what a is, well, it's negative 5 that makes x plus 5 0. And so we get 9 is equal to a times negative 3. And again, this term goes to 0. So a is negative 3. And if you look back at our previous work, that in fact was the integral that we did, right? We had negative 3 over x plus 5 plus 4 over x plus 2. All right, so your first exercise is to compute this integral using partial fractions. So again, you should be looking at turning this into something over one factor, x plus 5, plus something over x minus 2, and then trying to solve from there. That should be an easier integral. Okay, so I said that previous thing worked for distinct factors. So what happens if we have a repeated factor? So here, right, we have 5x minus 2 over x plus 3 times itself, right? So these are not distinct. Well, let's just try and see what would happen. So I'll put a big question mark here. Can we write this as something over x plus 3 plus another, constant over x plus 3? Well, no, right? Because what would this be equal to? Well, these have the same denominator, so we could just make this a plus b over x plus 3, which is a constant. And so suddenly we've canceled a factor of x plus 3, but x plus 3 is not a factor of 5x minus 2, right? So this does not work. On the other hand, what we can do, what is true, is that it will be some constant over x plus 3 plus some other constant, not over x plus 3, but over x plus 3 squared. So essentially, for each power of your factor, in this case x plus 3, you'll get a constant for each power of them. Okay, so we start with this. Again, we want to solve. Let's clear the denominator first yet again. So we're going to get 5x minus 2 multiplied through by x plus 3 squared. We get a times x plus 3 and then plus b. So the issue, right, is there's no factor over here that we can make 0 to get rid of b, right? We can only do that with x equals negative 3. So let's at least do that first. Let's make a disappear. So here we have negative 15 minus 2, so that's negative 17 is equal to 0 plus b. Okay, so b is negative 17. But how do we figure out what a is? Well, we can just substitute in, right? So, all right, we have b now. We have a times x plus 3 minus 17. Okay, I can add that over. Let's add 17, so it's 5x plus 15 is equal to ax plus 3, a times x plus 3. Well, this is just 5 times x plus 3 over here, right? So if we divide by x plus 3, we get exactly 5 is a. Okay, so what do we do here? We substituted back in for b. And then we just match these up, right? This is a linear term, this is a linear term, and we just see what we need. If you don't see the division as easily, another way you could think of this is 5x plus 15 is equal to ax plus 3a. And if these are equal, right, like this is my only x term here, 5x, this is my only x term here, ax. So a has to be 5, otherwise there's no way these could be equal. All right, for your second exercise, I want you to express this rational function, x minus 4 over x minus 2 squared, as partial fractions. So by partial fractions, right, that is just what we're doing, that's splitting it up into a sum. And so in this case, with a repeated factor, you know it should look like a over x minus 2 plus b over x minus 2 squared. So I want you to find the a and the b that make this. And now we will do one last example that takes care of these irreducible factors. All right, so let's suppose we have x squared minus x plus 6 over x cubed plus 3x. Then we factor our denominator so we can figure out like what fractions we would like to have. And we get x squared plus 3 here. And we know x squared plus 3 cannot be factored, right? So this is one of those irreducible quadratic factors. And so what happens here is we again have our a over x, but then it's not just some constant over x squared plus 3. Since this is a quadratic, in fact, we are going to have some bx plus c, some linear term over the quadratic. Okay, and so we need to solve for a, b, and c. But our strategy will be the same, right? So we want to multiply through by this whole denominator. So we'll get x squared minus x plus 6 equals a times x squared plus 3 plus bx plus c times x. And so now you may look at this and say, okay, I can plug in x equals 0 and I can get like the a term kind of by itself there, but there's no way to make x squared plus 3 0. So the best route here is actually to multiply this all out. Okay, so we're going to get ax squared plus 3a plus bx squared plus cx. And what I'm going to do is I'm going to match my x squared, my x, and my constant terms. I'm going to look at their coefficients and match them. So I'm actually going to gather my x squared terms together. I get a plus bx squared plus cx plus 3a. Now these things are always equal. So my x squared, my 1 has to match with a plus b, as coefficients. Cx, we have minus x. So c must be -1. And then we have 3a as our constant, and we have 6 as our constant. And so we have 3a equals 6, or a equals 2. And once we know a equals 2, then with a plus b equals 1, we get 2 plus b equals 1. So b is -1. And so now we have all three. We have our c, we have our a, and we have our b. And so repeated factors, we have to include more terms, one for each power that we see appearing. The distinct factors, we just split apart. They each appear once. And with a quadratic factor, we have to have a linear term up top instead of a constant term. And now we can pretty much take care of any rational function that we want to integrate. All right, thank you for watching.